I should get started since okay, so I was going to give a sketch of this theorem that every Hardy field can be extended to has a differentially algebraic Hardy field extension, which is Liouville closed, omega free, and Newtonian, right? Has all the good properties. And last time we the sketch got to the following point. I can already assume that my Hardy field is Liouville closed and contains all the real numbers and is omega free, but not yet Newtonian. So then we need to construct just one proper differentially algebraic Hardy field extension. And well, the fact that H is not Newtonian, the assumption that H is not Newtonian gives us a hole, right? So that's a triple capital P Godic M F hat, where capital P is a non-zero differential polynomial, and Godic M is what we think of as a monomial, but it just means it's a non-zero element of H. And F hat is in an immediate extension H hat, but not in H itself, and it's a zero of this differential polynomial. P F hat is zero, and F hat is strictly dominated by Godic M. Right, so H hat is an immediate H field extension of H. And I should emphasize it's not necessarily a Hardy field extension, because if that were the case, we would already be done, right? It's just an abstract H field extension. And now we can always take such a hole of minimal complexity, we call it a minimal hole, which means that if you take the order R of P, and then the second number is the degree of P in the last variable, YR, the highest order variable that occurs in it, and then the degree of P, that should be minimal in the lexicographic ordering on n to the 3. Well, n R has to be greater than or equal to 1, and it follows from this minimality that H is R minus 1 Newtonian, and that is a very useful thing to know, because that has the consequence that we know exactly how the H field generated by F hat over H looks like. Namely, it's isomorphic over H to the fraction field of this, they take these polynomials in y up to yr mod out by P, and then which is a differential field, right? Because in fact P is irreducible. One can, the minimality of P implies that P is irreducible. So this makes sense. And yeah, we can also arrange M is 1 by multiplicative conjugation. You simply replace capital P by capital P subscript cross Godic M, and then you replace M by 1, and you replace F hat by F hat divided by M. Right, and there are also other conjugations that are very useful, like additive conjugation and compositional conjugation. But for now, it's just M is 1, which means that F hat is infinitesimal. F hat strictly dominated by 1 simply now means F hat is infinitesimal. So now it will be enough to find a H Hardian F, that means an F that lies in a Hardy field extension of H, which is not in H itself, right? But what, in fact, we use F hat as a kind of guide to guide us towards finding an H-Hardian F which generates a Hardy field over H that is isomorphic to the Hardy field generated by, the H field that is isomorphic to the H field generated by F hat over H. Right, and then automatic, yeah. Okay, so at the minimum, this means we have to find an F, maybe not in H-Hardian, but something that is in this ambient differential ring, very big differential ring, which is not in H and satisfies this differential equation. That is a minimum kind of thing to do. And for that, and here we can, to do that, we can use a fixed point construction. So that is what I'm going to explain next. So for this we use fixed point, which is how you often use, which is how you often solve differential equations. Right, so here we go. We take the degree 1 part of P, or more precisely, we take the linear differential operator that corresponds to the degree 1 part, yeah, corresponding to the degree, the homogeneous degree 1 part. P1 of P. And now one can replace this minimal hole by various minor tricks so that this degree 1 part is actually also of order R, and that means that A is of order R. Yeah, so can replace our hole, our minimal hole P1 F hat with a minimal hole with A. To arrange, yeah, the new minimal hole, I'll just keep calling P1 F hat. We have to do so many replacements and conjugations. I can't keep introducing new names for the hole. So I'm just arranging here that the order of A, the new A, but I'll call it, is also R. Right, so okay, so now we make a bold assumption, yeah, a bold assumption, which simply to make the story possible, and then I'll amend it later on, but let's assume that this actually splits over H. Yeah, so A factors as delta minus V1 or delta minus VR. As a product of order 1 factors, and H is here an element, is simply a non-zero element of our Hardy field. Okay, so this of course is isn't fully justified, but I'll show you, but we'll come back to that. Yes.
For the replacement, what kind of operation did you use? Additive conjugation?
Yeah, at the moment I don't even quite remember, but there are indeed little tricks like additive conjugation, multiplicative conjugation is probably enough to arrange this. I would have to look it up now, but possibly, well, yeah. Right. So by twisting and other conjugations, yeah. So that's another. Yeah, I think I mentioned this twisting last time, and other, well, let's say other tricks or other conjugations. These are all we can arrange that all these phi's are asymptotic to 1. Can arrange, well, first of all, of course, I didn't mention that, but this differential polynomial p, you can always multiply it by any element, any non-zero element of h, and that won't change anything, right? So we can always arrange that the coefficient of lowest valuation of p is asymptotic to 1, and then we denote it this way, right? That means all the coefficients are of p are bounded, but one of them is actually not infinitesimal, right? That's another way of saying this. But more importantly, and all Vj are also asymptotic to 1. So again, that means bounded, but not infinitesimal. Yeah, again, that is a it takes some work, but again, this is just a sketch, so just believe me. And now we are going to go to the analytic part. The thing is that we now represent the coefficients of p and these Vj by actual functions, right? So represent. So these are germs, the coefficients of p and the Vj's, but at this point we have to take representatives and the Vj by functions which we can take to be, well, we can take them n times continuously differentiable for any n we like, but R is enough here, R the order of P, right? For a suitable real number A. Remember, this is simply the ring of, or the vector space over R consisting of the R times continuously differentiable functions on the interval from A to plus infinity to R. Yeah? Right. So, yeah, bounded functions actually. Bounded in the strong sense that this R norm, right? It means, yeah, that not only f, not only the function itself, but also its derivatives up to order R are bounded. That's what this bounded means. Which is very strong boundedness. Right, because we are in a Hardy field. Yeah, that's another thing, of course. In a Hardy field, if an element is bounded, then all its derivatives are automatically also bounded. So that that makes this right. So in fact, if these functions are just bounded in the ordinary sense, then the derivatives up to order R will also be bounded. So that's not really a problem at all. But now Vj asymptotic to 1 means that eventually Vj is greater than equal to epsilon, or eventually it's less than equal to minus epsilon. And that is exactly meaning that we are in the attractive or repulsive case. So and we take A so big that this happens. So every Vj, every factor delta minus Vj is either in the attractive or repulsive case, which I explained last time. Repulsive case. And that was what made it possible to come up with a well-behaved, that means continuous right inverse to this operator. So this yields, or this gives us a good, well, means at least continuous, but there are actually some other things that one would like to have, but I'm not going to get into. A right inverse B of this, where we now consider A as an operator on this Banach space. Oh, this goes to just bound, right? Yeah, of course, if you apply this operator to an R times continuously differentiable function, the result will not be necessarily continuously differentiable of any order anymore. It will just be continuous, right? Right, and B goes the other way around. And the nice thing about part of being good is that B is that both operators are continuous on these Banach spaces, right? And now we consider the following.
Sorry, now.
Yes.
And then this the opposite that goes from continuous to R bound.
Okay.
Sorry, A.
Yeah, yeah. B goes from here to here, but A goes, yeah. Yeah. No, you're right. Yeah, consider the, well, in general, nonlinear operator. Well, F goes to B of AF minus, well, yeah, maybe I should write P1F. Of course, AF and P1F are the same thing, but since I write here, right, so what does this do? This goes from, I plug in a bounded, strongly bounded in this norm sense. If I compute these things, it will be just continuous bounded. And then I apply B, so it then goes back to this. So this goes to CR. So this is now right. Yeah, of course B is linear, but this part is not linear. It's just the difference between P and its linear part. And the point is now that the fixed point of this operator will be a zero of capital P. So any fixed point of this operator will be a zero, is a zero of F. Of P. Now that's quite easy to check. What does it mean to be a fixed point? Well, B, it means F equals B of P1F minus AF. Now apply A to both sides. Yeah? Applying A apply A to both sides. What do we get? We get AF equals, well, if you, the point is if you apply A, then you get AB, but AB is the identity. So you get P1F minus, well, wait a minute, what did I write here? PF, right? PF. But of course, P1F and AF are the same thing, that's just a difference in notation. And so we get, so PF is 0. So this is how we converted our differential equation P f is 0 into a fixed point problem. And now the thing is, since we are now dealing with an operator on a Banach space to itself, we there is this very useful fact that if you have a contractive map on a Banach space or on some, you know, closed ball on a Banach space, it must have a unique fixed point, right? So so enough to show to get this fixed point, to show that above operator is contractive on say the closed ball, the closed ball consisting of all the f's and the functions in this Banach space. Our norm is, well, it turns out that a half is works, right. Contractive, yeah, if you have a function from a metric space to itself, you say it's contractive if if there is some r, if there is some rho strictly less than 1, positive rho strictly less than 1, such that p fx minus fy is the distance is less than r times the distance between x and y for x different from y, for all x different from y. And then you have, if the metric space is complete, you have a unique fixed point. Okay, and so now this can actually be arranged, this contractiveness, provided you increase A enough and you are able to first transform the whole, this whole into a certain normal form. Yeah, so this can be done. After first, yeah, I mean, this doesn't really work for in the situation that we have arrived at without further normalization involved. So after first transforming, and I didn't transforming, again, this is just a sketch, P1F hat into a certain normal form, which is called split normal, which we call split normal, normal form, or strongly split normal even, through successive, yeah, and this involves through successive yeah, manipulations, basically additive, multiplicative, compositional conjugations in every step making it a little bit better. conjugations can also involve no other little things, but well, to arrange that P is really very close to P1, or degree 1 part. In other words, it's P1 plus R, with R tiny compared to P1, or compared to P itself, compared to P1. Yeah? And I'm not going to explain. This has a rather technical definition. It's not that we actually use the word tiny in our definitions, but think of it as R is very is a very small perturbation of this P1, so to say. It's almost, P is almost like a linear, but it's much stronger than just quasi-linear. Right, and so a lot of our work is actually is really this, to come up with the right normal form, where one has to do a lot of experimentation to find the right definitions. Okay, and then, yeah, there's also, you see, we have the freedom of increasing A here. If we increase A, of course, then you have to replace all the functions involved, the coefficients of these P and the Vj, by the restrictions to the smaller half line. But you right, and increasing sufficiently increasing A. Okay, and you get for free that well, of course, the R norm being in half means the F and all its derivatives up to order R are less than or equal to a half, but in fact, one can show that F is infinitesimal. Yeah, we get F for free, and also an NF. And if you set it up right, basically you aim for F to be sufficiently close to F hat, right? Well, F hat is in this immediate extension, so can be approximated by elements in H itself, and you approximate and you let F also be close to the approximating elements. And anyway, if you do that, you get this for free. And so but then you get, and so we do then achieve our goal of finding a germ which satisfies our equation. Yes.
That you will still find a fixed point in this ball, but it will turn out to be infinitesimal, or do you mean that you will still be working in the same in the same ball, let's say changing A of same radius, but the fixed points will turn out to be infinitesimal?
Well, after well, not the A that I started with, perhaps, but after increasing A.
But taking a fixed A sufficiently large, or are you saying that you keep increasing and
you keep increasing till this works? Does that make any sense? You can indicate, yeah.
But
okay.
this working is just this operator being contracted on this ball.
Yeah, this contract achieving a contractiveness may also involve sufficiently increasing A. That's right. Yeah. This is all pretty vague, right? I only give a very very rough sketch. But right, of course, at some point you have to fix A. You cannot increase this all the time, but at some point A should be smaller, should be big enough so that everything that I say actually works.
So
yes.
The fixed point you get is in CR.
That is why I explained last time that if you have PF, you see, I had a little section last time that if PF is 0 and P has coefficients in C less than infinity, and F is only of order R times continuously differentiable, then F is actually also in C less than infinity. Yeah, that is why I did that first. So that is not really, that's not a problem anymore. But you're right, that is of course a point to take into account. That has to be addressed. But for, yeah, so that is one of the lucky things that one has to right. Okay, so let me say, yeah, the required normalization, that is really a fairly long story. But there's also an extra resource that I didn't really mention. I mean, there are lots of little things that I'm sweeping under the rug, but there is an extra resource. Here I pretended that A is just the corresponds to the degree 1 part P1 of P, but really it's enough for A to be close to. You can always perturb A a little bit so that this, well, how shall I say that? Maybe let me look. Yeah, can replace A by suitable. Yeah, perturb A little bit by suitable perturbations of it. You just add to A a small term. Of course, that will mean that here P1 also gets you add to A a tiny term, right? P1, that means corresponds to adding to P1 a minor a tiny term, but that will still keep R tiny, right? If you add here a tiny term and you subtract the tiny term from R, then the tininess of the remainder will still be maintained. And so I didn't really need that A here corresponds exactly to the linear part, to the degree 1 part of P. It can just be close to it. Yeah, by suitable purpose. Yeah. So that is another thing that you can exploit.
So you mean still a linear operator?
Yeah, still a linear operator. Yeah, sure. It's still a linear operator. But for example, the original A might not split, right? But it could well be that by adding to A something small, it will split. And then you're still in business. Okay. So, but now I'll mention the several problematic issues with all this, right? Yeah. Three. I'll just list three. There are certainly more, but 3 problematic issues. First of all, there is this bold assumption. That's of course a problem. It might not. Bold assumption might fail. Bold assumption. Might fail. Um, yeah, what we really need is to work all the time, not over H, but over its algebraic closure, HI. Yeah. Yes, we really, so this whole sketch, we really need to work throughout, uh, over HI. Yeah, that's the H is real closed, so HI is algebraically closed. And now this is still a differential field. The derivation extends uniquely. It's not an H field, but it has, you know, we developed this whole theory in our book in much bigger generality than just for H fields, namely for asymptotic fields and so on, and devalued fields of H type. And anyway, there are various categories of value differential fields for which the whole story with Newtonianity and omega free, etc., makes sense. And so, and that certainly applies to this one. Right. Over HI, and then with minimal holes, and really we have to work throughout with holes over HI. Right here we fix the hole. Yeah, one thing is H is not Newtonian is equivalent to HI being not Newtonian, right? So that doesn't make any change. HI being not Newtonian means that there is a minimal hole over HI, where the differential polynomial is now over HI. So with minimal hole. So the whole story should really be done from the start, working over HI with minimal hole. We have had over HI, but let me, and now with now, so P has now coefficients in here, and but now F hat will be in H hat I, but not in HI. And H hat is still, but H hat is still a minimal, sorry, H hat is still an immediate H field extension. Right. H hat, an immediate field extension of H. Yeah. And the whole, this Banach space, of course, you have to work with the complexifications. Right. And with the Banach spaces. These are no complex Banach spaces, of course. Complex Banach, Banach spaces. C, R, A, bounded with I adjoint. Right. And yeah, to really work with this in a way that works, you need to assume also that H is closed under taking cosines and sines of bounded elements. Also, but again, we could have assumed that from the beginning. Yeah, we already know that we can always adjoin these things. Also need to assume that, as we may, that sine H, cosine H in H are all bounded. H in H. Right. It doesn't follow just from Liouville closed, but we know that we can always extend H that way. Now the thing is, then we get since again the minimality of this whole over hi then tells us that h hat I is r minus 1 Newtonian again. So a lot of the story I told works just as well for hi. It's again hi r is greater than equal to 1. hi is r minus 1 Newtonian. Yeah, omega freeness is also preserved. Oh yes, for hi. Of course, I didn't define these notions for such objects, but they can be adapted. They really are defined in a more general setting than just for H fields. Yeah, by the way, and it's now the thing is that since now the constant field is algebraically is C, yeah, the constant field using that the constant field C of hi algebraically closed, one can now show that this splitting, this bold assumption is actually all right, or can be made to work for hi. Constant is algebraically closed. Yeah, especially r minus 1 Newtonian is now so strong. It's much stronger than just saying that h is, you see, this is much stronger than saying that h is r minus 1 Newtonian. It's so strong that it gives you this splitting. One can show all operators in hi delta non-zero operator split over okay, so that is so this is one thing. Now, good. Yeah, the problem is the next issue that arises is, but how do you get back then? You see, then you produce, carrying through this whole thing, then you find a solution in C infinity I, not in C infinity. Yeah, right. So how do we get back? So the second issue, problematic issues, is how do we get back? How do we get back working over hi to results to what we want for h. We want h. Let me make that a little bit more concrete. Yeah. Say we have f in C I, Pf is 0. Well, I'll say f not in Ci, not in Hi. Say we can achieve that, but of course, what we want is a function or a germ in this without the I. So now we have, of course, now you can write. Sorry.
We were just wondering how you get this splitting of order R with the R minus 1 Newton.
Well, it's just a general fact that if you have an R minus 1 Newtonian, algebraic closure of an H field, if you want, which is then all operators of order R. I forgot to say of orders less than or equal to R. Is that? Yeah, what I say is of course ridiculous, but of R minus 1 Newtonianity, it means you can solve a lot of differential equations of order at most R minus 1. Now, if you have an order R operator, linear operator, you can, there is this Riccati construction, which replaces it by an order R minus 1 differential polynomial. And there you can apply the R minus 1 Newtonianity, giving you a zero of this Riccati polynomial. And then you can use that to factor this, to split off one factor, and then it will be of lower order and so on. Yeah, good question. I could have mentioned that. Right. So of course we have F. You can write F as G plus HI. Yeah? So G and H are in C. So G and H are simply the real and imaginary parts. So the idea is that, well, F satisfies a non-trivial differential equation over HI, and then you can show that G and H will satisfy also non-trivial differential equations over H. And one of them, G, since F is not here, is not in HI, either G will not be in H or H will not be in H. Yeah? So G not in H or H not in H. And then want to show let's say that either this one or that one, G or H, is H Hardian. Yeah. And then we would again be done. The problem, this is very tricky. I can't even really explain how we are doing that. It just, we can do it, but right. Yeah, tricky. Let me just write. Yeah, so this is the second issue, which is I think too complicated to explain in a few minutes. But and then the third issue, is, well, suppose suppose we ultimately do construct a, yeah. Oh, I see. I'm already out of time. Okay, then I'll stop here. Thanks. I'll mention this just next time at the beginning, and then I will go to a new topic that is related to 2. I will still say a bit more about 2 because, but it's more self-contained, and I can state some very nice facts related to it. So that will be on Thursday. Yeah, time is going faster than one expects if one doesn't look at the clock. Oh yeah, we